All right, 725 grams of water at 65 degrees C. Has anybody ever used a hot water bottle? I just learned about these things the other day. I didn't realize this was a thing. But it's not like a bottle. It's like a squishy, plasticky kind of a bottle, and you put hot water in it, and then you put it in bed with you or something, and it keeps you warm. Or you put it on sore muscles or something like that. Anyway, so in this case, you have 725 grams of water in this thing at 65 degrees C. The water cools to body temperature, 37 degrees C. How many kilojoules of heat could be transferred to sore muscles? So you need to use something called the heat equation, which we haven't gone over, but it looks like this. Heat equals, well, let me see exactly how they wrote it in the book, because there's a couple different ways we can look at this. I just want to be consistent here. Okay, yeah. So they write it like this. Mass times delta T times SH. So this is, let's annotate this. And that's the mass of what's being heated. So the mass of, in this case, heated or cooled. So the mass of water in this case. This water is cooling. That's not always going to be the case. It depends what the question is asking about. This is going to be the change in temperature, degrees C or K. So we'd find that by subtracting the initial temperature from the final temperature. So whatever temperature it ends at minus whatever temperature it starts at. The other way you can think about this is just the difference in temperature, the change in temperature, kind of the absolute value of the change in temperature. Then you have to think about the sign in terms of negative or positive if it's exothermic or endothermic. But if you just do it this way, you'll always be fine. And then SH specific heat. Specific heat changes from material to material. We talked about that last week. For water, which is what we have here, it's either 1 calorie per gram degree C. That means it takes 1 calorie to raise 1 gram of it, 1 degree C, or 4.18 joules per gram degree C. You don't have to remember that joule number. You'll always be given that, but you should know the calorie one, the 1. So if we put all the units together, we can figure out what our final heat units should be. So our final units of heat should either be in calories or joules or some kind of heat measurement, energy measurement. All right, so in this particular problem then, that's going to be the mass of water, which is 725 grams, times the change in temperature, which in this case is 37 minus 65, times the specific heat, which we can use any of the numbers we want. Since the question is asking for kilojoules, probably makes the most sense to use the joule number here. If we simplify this a little bit, 37 minus 65 is negative 28, right? Yeah. So we now have grams, degrees C, and those cancel with the specific heat. So grams, grams, that's why we have the grams and degrees C on the bottom. degrees C, degrees C. That means we're left with joules. Calculate this out. That's 725 times negative 28 times 4.18. I'll just round it off here. All right, now that's joules. The question asks for kilojoules, so we need to divide that by 1,000. So minus 84.9. We'll round it off again, kilojoules. Or if you just wanted to say 85, that's fine too. 5 kilojoules. Okay, a couple things. First, is it important that that be negative? For our purposes, no, doesn't matter. If you report that as positive or negative. The negative tells us which direction the energy is going. So the energy is going away from the hot water bottle, away from the water. So it's exothermic from if your system is the water. But if you're thinking about your body, then it's endothermic because the heat is going into the muscles. So, and then the question itself says how many kilojoules of heat could be transferred. So it doesn't say how many kilojoules are emitted or what is the energy or something like that. So it doesn't care if you have negative or positive, is the answer. I don't care. You don't have to be careful about that here. You can simply take the difference in temperature and do that calculation. Right, but this is how you do a typical heat calculation like this. And you'll be doing this in lab tomorrow. I think there's some pre-lab exercises to that effect as well. All right. Let's look at what happens when there's a similar type of problem, but dealing with a phase change instead of just a change in temperature. So in that example, we changed the temperature, but the water was still water. So let's look at what happens when you go from ice to water, or water to steam, or the other way. Okay. We'll look at another example. I don't really want to do that this way. So these challenge questions, I'm not sure if they're listed. Are any of these listed in the homework? I don't know if anybody saw them, but these are not, what? 3.85 to 3.88. Okay, but not more than 3.88? No. Okay, good, okay. So yeah, these down here are a little bit tougher. We're not going to look at those types of ones in this class. Okay. Let's look at a problem that deals with a change of state here. Because we will deal with changes of state in lab tomorrow. All right, ice cubes at 0 degrees C with a mass of 26 grams. So 26 grams of ice total are added to your soft drink. How much heat in joules will be absorbed to melt all the ice at 0 degrees C? So in this case, the ice isn't changing temperature, but the ice is melting. So we have to figure out how much energy is being released. Now these types of problems, when there's just a change of state and nothing else, these are actually a little easier because they're really just a conversion unit type problem. And let me show you how that works. So we start with 26 grams of ice. we want to have a factor that gets rid of our mass unit and instead gives us an energy unit. So we want to know how much energy does it take to melt a gram of ice, and that's our number here. Since it looks, so we can look at those numbers. Okay, the heat of fusion of ice, which you don't need to memorize, is 334 joules per gram. That means every gram of ice takes 334 joules of energy to melt. So 334 joules per gram. So all that ice takes 8,684 joules to melt.
I have a question out of curiosity, because in the book it wants you to round it. So would you round the 8 or would you round the 6?
It's always a weird question in this class because we didn't go through that section in the first chapter about like how do you know which one to round. So the answer is whatever you like. And I won't ever mark anything wrong just because it's rounded wrong.
So you want us to round or no?
It's up to you. I don't want you to write, if you plug something in your calculator and it gives you like 30 decimal places, don't write all those. Just pick a couple and round it off.
Okay.
If it's easy enough to leave all the numbers there, then fine, leave them there. Okay. Usually our rule of thumb has been however many significant figures are used in the problem itself, stick with about the same number in your answer. Because again, we didn't go through those rules. So in this case, 26.0, that's 3. So, yeah, if you want to leave that like that, or if you want to round it 8,680, it doesn't really matter. Whatever you like. Just to make it reasonable to work with, You don't want some crazy number of a bunch of stuff. If it really bothers you, just go read that section in chapter 2 and you can figure out the rules, but you don't have to worry about that. Okay. All right. So that's all there is to that. Any phase change is going to be the exact same calculation. The only thing that changes is the number. So if you're dealing with, let's say, vaporization instead, same calculation, but instead of 334 joules, it's going to be whatever the heat of vaporization is. 540 calories is about, I don't know, whatever that is, 2,000 some joules. Does that help? Does that make sense? And there are some problems like this for the lab tomorrow also. Let's answer the other one just because it's interesting. What happens to the temperature of your soft drink when you add the ice to it at 0 degrees?
The water will change, the ice will change.
Yes, but what happens to the drink, to the temperature?
Temperature is
The temperature decrease, right?
Yeah.
Yeah, it goes down, it gets cold. Why?
Because the degrees, it have or like the ice take the energy inside.
Mm-hmm.
So
That's right.
it's make it.
Yeah, because that energy, that 8,684 joules, has to come from somewhere. And that energy is coming from the drink, the liquid that it's in. So it's pulling energy out of the drink, making it colder. Anything that becomes colder, energy is leaving it. So when you touch something cold, that's because that thing is pulling energy out of your hand. So that makes it feel cold. That can help us think about exothermic, endothermic, and that kind of thing too.
I have a question about the energy. I thought the energy is coming from something hot, not from something cold to us.
That's right.
So how you say like, when I touch it, that's when it will come in my body.
Well, you have to think about where the energy is coming from. If you touch something and it is hot, it is because energy is going from that thing to your hand. If you touch it and it is cold, then that means energy is going from your hand to the thing. But if you also consider the environment around, maybe it's different. So every situation might be a little bit different. So you have to think carefully about what you are looking at to determine which way the energy is going. But we're going to do this in lab tomorrow. We're going to do a couple chemical reactions, one of which is exothermic and one of which is endothermic, and you'll feel what that difference is. All right, other questions about problems from this chapter, these kinds of things? All right. I wanted to look at another problem that we didn't have a chance to at the end yesterday. Looking at heating curves. Not finding it. Okay, maybe not. Maybe I was thinking of something else. Okay. So for this chapter, you should be able to do those basic heat calculations that are in the homework, but you don't need to combine them. What you'll find, as long as we're looking at this, if we look at some of these more difficult questions. Oh, okay, that's one. We'll come back to that in a second. Some of these more difficult questions, like take a look at this one. A 45-gram piece of ice at 0 degrees is added to a sample of water at 8 degrees. All of the ice melts, and the temperature of the water decreases to 0. How many grams of water were in the sample? That's a very difficult question. We're not going to go through it. But the idea here is that multiple things are happening in sequence. So you have heat exchange happening from something melting, which was the second thing that we did. But you also have heat coming from a change in temperature. So you can have heat transferring in two ways, either changing the state or changing the temperature. And those can happen at the same time, so you can actually have to do both of those. There's a couple problems in the post-lab part for tomorrow that deal with that ask you to do those calculations. Don't be scared from that. We're not going to have those kinds of questions on quizzes and exams. I don't know why they're in the lab that way, but they are. So if you're having trouble with that tomorrow, we can work through it together on Thursday in class also, because those won't be on the exam. But I did find the other question that I was thinking of. One thing that we can do with heating curves, we looked at heating curves of water, but we can also look at heating curves for non-water things. So you might have done this one in your homework. Let's look at it together. We're looking at a substance called benzene. Has anybody ever used benzene before? No. It's a solvent, actually. It's used to dissolve things. It used to be common in paint and that kind of thing. It's a carcinogen, so we don't use it that much anymore in terms of in public use. But it was used really a lot for a long time. People who went to college in the 60s or 70s probably washed their hands with it and all that kind of stuff, and now we don't do that. But that's benzene. So here's benzene. And benzene has a melting point of 5.5 degrees C, so higher melting than water. And a boiling point is 80.1 degrees C, lower than water. Sketch a heating curve for benzene from 0 degrees to 100 degrees. So I want you to try this now. I'm just going to remind you, this is what a heating curve looks like. You're looking at what is this thing doing at each temperature as you add energy in. So the x-axis is heat absorbed, the y-axis is temperature. We can start it together. Temperature in degrees C, and we're starting at 0 to 100. So knowing only those two things, that the melting point is 5.5 degrees C and the boiling point is 80.1 degrees C, we should be able to come up with a heating curve for benzene. Let's see if you can draw one. Everybody got a heating curve? Looking pretty good. All right. So how did you figure out where to draw the lines here? Looks good. Yeah, we're going to look what's going to happen at the melting point and the boiling point. Well, yeah, it's flat, right? It goes flat because at those points, the material absorbs energy but does not change temperature. So let's see if we can find that on the graph here. 5.5 is, all right, we'll make it a little bit bigger. Call that 5.5, and then call this 80. So something like that. Now, we can't know, well, let me rephrase that. How do we know how long to make those lines? How long to go horizontally? We don't, but how could we maybe know? Yeah, but if let's say if we wanted to like look something up, is there a way to know that? What does that quantity represent? What?
I think I count.
Like, well, the length of those lines is the amount of heat that it takes to do that phase change. So that's what we call either the heat of vaporization or the heat of fusion. So a big heat of fusion would mean that that lower straight line, this one, would be longer for a big heat of fusion. A big heat of vaporization means this one is longer. Small would be shorter. That information isn't given here, so we have to just guess. It just doesn't matter how long you make them. What else could we find out about that we don't know about? The slopes. So how do you know how steep to make those lines? The lines that go up here and here and here. I made them all about the same angle, but how do we know if they're really steep or really shallow?
Higher number or short number?
What number?
Like to be sold and to be free.
Well, that's going to be the horizontal ones. But what?
CHM's length and hitting like wheel point, the length and depends and the melting point's length. So make
Okay, yeah, if those were to change. But if to get actually these slopes, that comes from the specific heat. So a low specific heat means it's easy to heat it up really fast. So that means the slope will get really steep. And a really high specific heat means it takes a lot of energy to heat it up, and that'll make it more shallow. So again, that information is not given here, but we could look up the specific heat of liquid benzene, solid benzene, gas benzene, and see what those numbers look like, relatively speaking. All right. Other questions about heat stuff? All right, we'll do this more in lab tomorrow, and we'll have our next quiz. Oh, which I forgot to bring the previous quiz, but I'll get it to you tomorrow. Yeah, so the next quiz will be Tuesday, a week from today, on this heat stuff in this chapter. Okay, let's move on and talk about some atoms. New. Oops. Okay, we're gonna jump into the next chapter. And I want to pull down a somewhat familiar figure here. This one. All right, has anybody ever seen this before?
Yes.
I hope so, like right there, been there the whole time. So let's talk a little bit more about what this means and how this thing is organized and all of that. So this is, of course, the periodic table. It's a list of all of the elements. And we learned from a couple weeks ago, last week, I don't remember, that what is an element? It's a type of a pure compound. What's a pure substance? What's the difference between an element and a compound? Well, careful, because mixtures are a different thing.
Compound is
Made up only from one element and compound from two and more.
Yeah, an element is made up of one type of atom, and a compound is two or more types of atoms. So in a way, it's like a mixture, but we use that term mixture to mean mixtures of different pure things. A pure compound, even if it has multiple elements, multiple atoms, it's still considered a pure compound. So yeah, so we've got these different types of atoms that are kind of the basis for all of matter. And they're laid out in this kind of unusual way, unusual pattern. You know, could just be a list, but they're put in this particular table. And we're going to go through and kind of talk a little bit about what that means. Why is it laid out this way? What do these numbers on the table tell us, and so forth. So first, I guess, the first thing that's talked about in the book is splitting this up into 3 types of materials. You've got this blue section here, and then a yellow section here, and then these green ones kind of in the middle. And these are defined as 3 categories: metals, metalloids, and nonmetals. Why is that important? What is it that makes something metal versus a nonmetal? What's special about a metal? If I gave you some stuff and I said, is this a metal or not? How would you answer that question? What would you look for to see if it's a metal or not? Is what? Yeah, maybe. You can't see? Like, okay. Okay, so you can go with that. What else?
Conductor.
A conductor?
Would that make a difference between a metal and a non-metal?
Yeah, absolutely. Which one's a conductor and which one's not? I'm asking.
Oh, are you asking me which one? Metals are conductors.
Yeah.
Correct?
Yeah. Yep, so then we got a couple things here now. We can write some stuff down. So what's special about metals? Metals are metals conduct electricity. They're conductive. So if you pass a current through the metal, that current will flow through the metal without too much resistance. That's why we make wires out of metal, for instance, things like that. All right. Another thing that I think you were getting to is they are shiny. You can see a reflection in a metal, especially if you polish up the surface. The technical term for that is luster. They have a luster. That's that shininess. What else about metals?
Can you melt metals?
Yeah, but you can melt anything, pretty much. And the solid thing isn't necessarily true either, because you can always melt a metal and make it a liquid. And then some metals like mercury are just a liquid at room temperature. So they're not necessarily solid. But there is something else, another property that's special about metals.
The density,
What about it?
that it's greater than the other.
Maybe. Statistically, yes, but actually the density is more dependent on how big that is, how big the atom is. So anything toward the bottom is going to be more dense than anything toward the top. So very heavy non-metals could be just as dense as metals, although you're right, the heaviest things on the periodic table are all metals. Or the most dense things on the periodic table are metals. There's one other property. I'll give you an example. Imagine a car door, like a door of a car. You got the bottom part that's made of metal, and then you got the window, which is not metal. So what happens if you take a hammer and hit the window? It breaks, right? What happens if you take that same hammer and you hit the side of the car? It bends, right? It doesn't break, it bends. It kind of dents, it deforms. Yeah. That's an important, has anybody ever done that? You ever tried to wreck somebody's car with a hammer? No? Okay, I didn't know. I thought maybe you had a good story or something. Somebody made you really angry. Maybe after that first exam, I'll find some dents in my car doors. Hopefully not. There's already a lot of dents I might not notice. Yeah, so the technical term for that is that metals are malleable, which means they can deform without breaking. The reason for that has to do with the electrons in a metal, the structure of where the electrons are. In a metal, we often think about the electrons as being spread out among all the atoms rather than being localized on particular atoms, whereas in other structures, the electrons are more stuck with the nucleus. So when you hit something that is not malleable, the atoms have to break apart from each other and the electrons stay with themselves. But when you hit a metal, the electrons can just spread out and fill the new shape and not have to break apart from each other. So metals are malleable, and that is unique to them, that if you hit a metal with a hammer, you can spread it out, you can flatten it, you can dent it, you can bend it, and you don't break it necessarily. Okay. So we would imagine the yellow ones, the nonmetals, are kind of the opposite of this. They tend to not conduct electricity. They tend to be dull and not shiny, and they are brittle. They'll break if you hit them. Now, that's not true for everything, and some of them are gases, so it's kind of different, but that's a good general sense of what the difference is. And then, of course, because nothing's that easy, you have these green things in the middle called the metalloids or semi-metals that are kind of half and half. So they have some properties of metals, they have some properties of nonmetals. And we're not going to get too much more into that other than just saying that that's what happens. One of the most important properties of those semi-metals is being what we call a semiconductor. Have you heard the word semiconductor? I don't know if you're familiar with that idea, but it's kind of what it sounds like. It's in between a conductor and an insulator. An insulator does not allow electricity to pass. A conductor allows electricity to pass easily. A semiconductor, it's sort of easy, but not that great. And the effect from that is that you can control the conductivity of a semiconductor chemically. And that's how all electronics work. Computer chips, all the stuff that makes your phones and all that good stuff work are made generally from silicon and germanium, which are these two here, because of their semiconducting capabilities and the way that we can control how electricity passes through them. So that's a big important part of a semi-metal, but we won't get too much more into that. Okay, let's talk about the symbols here. Let's just pick one. Let's pick carbon. If we look at the entry for carbon up there, now that periodic table doesn't have the names, but you'll always have access to a periodic table that does have the names. You'll see one number usually above the symbol, and then another number underneath the symbol. Does anybody know what those numbers mean? Yeah, it has to do with how many particles are inside the atom. Anybody know what atoms are made out of? Protons and neutrons and electrons. So let's take a look at those. Protons have a charge of +1. Neutrons are neutral, and electrons have a charge of -1. The number in the upper right-hand corner here is known as the atomic number, and it tells you the number of protons in that atom. The protons are in the nucleus, in the middle of the atom. So this tells us that carbon has 6 protons. Now, because a carbon atom, any atom in its neutral state is neutral in charge, that means it has to have the same number of electrons to balance out the charge of protons. So if this carbon atom has 6 protons, that tells you that it also must have 6 electrons. So the atomic number can also tell us the number of electrons in a neutral atom. This tells us it's a neutral atom. 6 plus, 6 minus is 0 overall. That's not always the case. We're going to look at what happens when there are different numbers of electrons. We call those ions. But notice what particle did I not say how many there are yet? The neutrons. Why not? Anybody know? How many neutrons are in a carbon atom? 6? How do you know?
Because there's the amount of neutrons as protons.
That's actually not true. I mean, it's true that it's 6, but it's not always the same amount of neutrons as protons. And that's why I didn't write it down. You can't tell the number of neutrons from the periodic table. There's nothing that really tells you that. You need something else. You need something called a mass number. So to get the number of neutrons, you need a mass number. And the mass number is the neutrons and the protons. So if I told you that a particular carbon atom had a mass number of 12, then you'd know, there must be 6 protons and 6 neutrons, because 6 plus 6 is 12. But if that mass number were 13, then it would be 6 protons and 7 neutrons. And in fact, both of those exist. They're given different names, and they're written like this. This example, where there's 6 protons and 6 neutrons, is called carbon 12, and this one is called carbon 13. Those are 2 different kinds of carbon atoms that exist in nature, carbon 12 and carbon 13. And the name for those is that they are isotopes. Isotopes have the same number of protons but different number of neutrons. And you can only figure out the mass number from either knowing how many protons and neutrons there are, or from knowing the mass number. The mass number is not given on the periodic table, so we can't figure that out that way. What is given on the periodic table is this thing, which is called the atomic mass. Now, we're not going to get too much into this, but if the mass numbers are even numbers or integers like 12 and 13, why is there this atomic mass that is usually some weird decimal? Yeah. Where does that come from? It's actually an average of all the existing isotopes. In nature, there is mostly carbon-12. It's about 99% of the carbon in the world is carbon-12. And about 1% is carbon-13. And then there's a little bit of carbon-14 also. So when you average those all together, you get a little bit more than 12. And that's what that number comes from. So that number is actually an average of all the different isotopes for all the atoms. The ones in parentheses, like you see kind of lower in the periodic table, those have no stable isotope. They're radioactive and they split up into other stuff. So I believe that the parentheses usually lists the most stable isotope, and that is a mass number because it's an even number. The numbers of the different isotopes are always changing because they're radioactive, so there can't be a nice average like there is with the other ones. All right, so let's practice this. We're going to take this table, which you're going to do something similar to this in lab next week. This is complete the following table for a neutral atom of each element. That is, if you had a neutral atom, some of the numbers are given. Enough is given here that you can figure it out. And then you should be able to fill in the rest. So let's look at the first one together. The symbol is Al. What's the name of that element? Anybody know? Aluminum. And what's its atomic number? 12. No. 13. Look at the periodic table, we find 13. All right. Now the mass number is given as 27. How many protons would that atom have? 13, because the atomic number tells us the number of protons. How many neutrons? How do you know 14? Yeah, because the protons plus the neutrons have to equal the mass number, which is 27. So 27 minus 13 is 14. And then how many electrons? Close. Nope. 13, yeah. That's right. In a neutral atom, so that's neutral, not charged, that means that the positive charges from the protons have to balance out with the negative charges from the electrons. So you have to have as many protons as electrons. And those balance each other out. All right, see if you can finish this up on your own. Finish this table. And then we'll take a look at it. Let me know if you have trouble. If you don't know the names for some of these, feel free to look them up in a periodic table. If you have your lab notebook or your book with you, those will have that in there. All right, I'm going to finish filling this guy in here, and then you can check yours. So if you're still working, don't look at what I'm doing yet, but finish up what you're doing. We'll go from there. Did I do it right? Where? Which one? S? Mass? Well, remember, that's an average. We can't use those numbers for the mass. We get the mass by adding the protons and the neutrons, and those are given. So 16 plus 15 is 31. So this particular sulfur is a different isotope than that one. One interesting example of that, if you look at bromine, number 35, Br, the mass is 79.9, the atomic mass. So you'd think, okay, well, the most common isotope of bromine must be 80, because that's really close to 80. But actually, there is no bromine 80. Bromine exists in 79 and 81, and they're about half and half in nature. So they average out to 80, but there actually is no bromine 80. So you can't use the periodic table to find the mass numbers. Any other issues on this table that you're not sure where I got some numbers, or did I get any wrong here?
I guess my answer is wrong.
Okay, do you know where you went wrong, or why?
Because I don't know the name, the third one. So I choose one for.
Oh, okay, yeah, you have to look it up on the table.
Yeah.
Look it up in the book or something, so you can. You don't need to know these names, by the way. I will always have for you, for exams and quizzes, you'll get a periodic table that has all the names on the back. So you can always look it up. No.
We can divide two, if we have a water number, just be plus it with the second number of protons.
That's right. The number of protons plus the number of neutrons is the mass number. Yeah. So like this last one, iron, you're given the mass number is 56, and you're given the number of electrons. So how do you find the rest of it? Well, protons must be the same as electrons because it's neutral. So that must be 26. And then 56 minus 26 is 30. So that tells you the number of neutrons. Then you can look up 26 as iron. We'll have some more practice to do this also. That's atomic structure. So I don't want to go into ions right now. We'll get into that more on Thursday. A little ahead of ourselves. So we'll stop there. I did forget, though, one thing, so I want to mention this. So lab tomorrow, and I'll post this on Blackboard, too, in an announcement. It's February 3rd. Instead of the beginning of lab, we're going to do something a little bit different, just because it happens to be going on at the same time. There is an event in Z102, which is the big lecture hall over there, across the hall. You know where it is, the one that kind of sticks out in the front there. There is an event from 12 to 1 p.m. about recycling at Harper. They're going to a new kind of a system of how we're sorting the recycling, and it will affect this class because we're going to talk a lot about plastics in a chapter later and the different types of plastics and why we use them and things like BPA and all those kinds of things. So it'll be really interesting to see what they have to say about plastics at Harper. And since this is really close to our lab time, I thought this might be a good thing to do before lab tomorrow. So I know some of you may have class or a conflict. Can anybody not make it at noon instead of 12:30 tomorrow? Or you're good? Okay, great. Then we'll start there. Oh, you can't make it?
Well, I have classes like 12:15.
Okay, so so by the time you get down there, it'll be 12:30 or something. That's fine. I wasn't sure if people had conflicts or not, but so when you're done with class, don't go up to lab. Come down here and just come in whenever you can. I figure some people won't be able to make it right on time. Otherwise, if you have that, you can bring your lunch, and then I think they're going to have cookies, so that's something. And we can learn about recycling and eat some cookies. Then when it's done, we'll go upstairs and we'll do lab. I've got a couple things that I want to cut out of the lab so that we make sure to have enough time for everything. So I will see you there tomorrow. All right, that's it. Let me know if you have questions or anything else. So lab tomorrow, regular stuff is due. If you haven't finished your questions online from last week, put those in before class tomorrow. There's a pre-lab before the lab, some heat type stuff.
Do we have to turn in the paper from last week's lab, or is it just all online?
No, you don't have to turn in any paper from last week's lab. It might be this week because you have to do some calculations that it says like show your calculations. So I'll probably collect something from this week, but nothing from last week. Yeah, so I'll see you at noon tomorrow over there.